happen.
He was talking about an menstrual cycle.
Yeah,
Oh, he's gonna be like, guess what? You picked up observations.
I had a feeling he was gonna do that.
Have you guys taken them?
Yeah.
Where's Alex at? No, it's here, bro.
Yeah, right.
That's weird.
Maybe he's with his child.
Which one? Does he? I never seen pictures. Oh, no. It's just the weekend. That's bad. I don't like that.
Yeah.
How about, yeah. Maybe Thursday.
This is Thursday.
No, that's Thursday.
Too bad.
Thursday,
Friday.
5 in the morning.
I like watching the daytime night.
Okay, that could work. Oh, there's fun. Okay, well, let's not. Okay,
All right.
now
That's not fog.
that's like actually.
This is precipitation.
Okay.
So this is rain,
Oh, we just read
light,
it.
moderate, heavy.
Okay.
Gives you a 2-day forecast.
Okay, so Thursday won't work.
So you're telling us, do not ask me to do observation.
How about Friday?
I don't want
Neither do
Well,
I.
good thing we're not with the same.
to. I'm thinking to myself.
I lost the game because money.
Which game?
The game.
Which game?
The game.
Which game?
The game that you can't remember.
Which game?
You remember the game. Yeah. How long has it been since you remembered the game?
I have no idea what you're talking about. I've never even heard what you're talking about.
Oh, how long has it been? Really?
Like a day?
Oh, okay.
Okay, that's fair.
No, the internet always reminds you.
Oh, yeah.
The internet. Ever heard of the internet?
Yeah. Cybernet, man. Skynet.
Nerd on nerd crime.
Yeah.
Summaries? What do you mean, no?
I just got it back. I can't do something back.
No, you have new summaries. New paper every week, new summary every week. New paper every week, new summary every week.
I like what I.
Okey doke. Are we waiting for anyone? Who's missing?
Oh, Alex is back here.
Thursday.
I don't know.
For what?
I don't know. We went to.
Oh, E&M.
Yeah, right. Is there
Yeah.
two homeworks for this week since?
Two problems. And they're straightforward. I won't say that they're easy to do, but intellectually, they're not complicated. They're simply reusing things that we've done. Okay, so this is the part of the class where I tell you, I told you so. Okay? So my urging the entire class long was to take observations early and often. And currently, we are starting what we call winter. Okay, winter is coming, the start words. So you're looking at zoom.earth, which is going to become your friend. Gives you very up-to-date predictions about what the weather is going to be like. You can also use, I prefer to use this, if I just want the day-to-day. So this gives you an update as to the current temperature. And tomorrow there'll be a wind advisory at night. So that seems very unlikely to be able to do observations. And Thursday nights is mostly clear. So maybe you can, convince someone that that is a good time. But of course, predictions change. right? So you always have to sort of hedge your bets on what could be going on there. Friday night also looks mostly clear, but you wouldn't really trust a prediction more than 2 days in advance, okay? Especially for clouds. You know, for temperature, is it going to be hot? Fine. But whether or not there'll be clouds and it's hot is unclear. This is the third thing to use. So you'll see tonight, this is the current time, and there's clouds. And unless you want to wait till after 9, which I don't, I don't think we'll be able to observe tonight. Another thing you want to look for is down here. This is the humidity. So if you have 75 to 80% humidity, that's the bumping of the air molecules. And so that's going to lead to really bad signals. Now it's going to clear up, right? So you look here, the humidity goes down, drops down really low to less than 25%. But that is due to this part here, which is the wind. So the wind is literally going to push the water vapor out of the system. So this looks like a pretty good night. You know, the wind stays 6 to 11 miles an hour. Humidity will be down to 25%. Thursday's potential, but we'll see how that shakes out. There's a limited number of weeks left, one of which I will be in Tokyo for, as many of you know. I think everyone in here knows, right? Okay. So that's just my, you know, you got to take these observations in order to analyze them. Okay. So today we're not going to talk about taking observations. We're going to talk about the physics that goes on behind it. The physics behind taking observations. So actually, I guess if you guys are continuing in your wind tunnel project, yeah, you may not need this. You're welcome to stay. We'll talk a little bit about Poisson project at the end, but generally speaking, we're going to be talking about how CCDs work and how they introduce sources of noise. Yep. Okay, we're going to talk about Poisson processes. So we're going to talk about how detectors create signal, right? And how those signals turn into uncertainties. Yeah. So I would say like 15 minutes to talk about the detector. So if you want to run and get coffee or you want to run and grab a sandwich, we probably won't start talking about uncertainties for another like 20 minutes. Okay. 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 Ready? Folks who are I'm actually talking to. Okay. So what is the primary physical mechanism responsible for our ability to turn light into a number? Yeah, so that's the machine that you build. Yeah. It's gonna raid my office for candy. Is that what's going on? Yeah. Okay. Okay. So the primary mechanism, we've talked about this a little bit. Let's see how far over I can go. Okay, that'll work. Okay. You have a bucket. Right? Yeah, photons go in. So this is the picture I want you to have in your mind. And that's the symbol for photon, it's gamma. Okay. And something happens in the bucket, and then you get a number out. So today we're going to talk about what happens in the bucket. Okay. Can you use any material to make a CCD? No, you have to use good and specific atom that we like. Silicon, right? So in fact, there is a band gap here. Okay. What does a band gap mean? A band gap says that in the structure of the atom, you have an actual discrete energy level, okay, that allows the valence electrons of silicon to be liberated as long as you add energy. Photons are energy. So what they're able to do in this substrate, the piece that is, this part goes out towards the sky, absorbs light in of a specific energy, and then electrons go in the other direction. Okay, so this is the photoelectric effect. Photo means light. Electric. Explaining the photoelectric effect was one of Einstein's first Nobel Prizes. Okay, so you can't make your selfie without making this. You can't make the camera that's on my laptop recording this without having this. So to understand this process, we have to understand that this means that the band gap that you use is tuned, right? So the size of the band gap is tuned to what property of the light? Right. Why? There's just one more word I'm looking for.
Oh, is it like?
How big is your?
So this band gap is a band gap in what property? Okay,
Electron volts.
yeah, so let's imagine that it's like this, right? Here's an electron, here's an electron. As I move up, I am
Excited.
right by what process? Okay, so
Yeah.
here's the photon coming in. The photon is delivering what? Energy. So this is an energy gap. Okay, the band gap is a band energy gap. So what property size here goes to energy, right? And energy for a photon, we say.
Please. That's,
Right?
Yeah.
It's frequency dependent or wavelength dependent. So I could just write C in there and I would have lambda. Okay. So the size of the band gap tells you what kind of photons you can absorb. So can I use a CCD to observe in the infrared?
I guess if it's gauged or that way, right? Like if you have something that can absorb that.
Red is big.
Yeah, that's a good question. So what has more energy? This is more. And this is
That
less.
is like
Let's say this is
700
visible.
meters.
Infrared is, I think, more about.
Yeah, the wavelength of red is like 780 meters. So
Our CCD is too small for infrared.
What property is too small?
Band gap, it's like
So does infrared have more or less energy than
what?
visible? Less.
Okay.
Okay, so infrared is not easily absorbed because
They have a really small band gap.
the electrons they don't have enough energy to make that jump,
okay.
right? So this is the jump that we're talking about. We're going from one state, absorbing light and moving to another state. The details of which we're not going to get into. That's a whole nother class. Okay. What if I have too much energy? Let's say an X-ray. What happens? What?
I just need to probably pull this down.
No, it also cannot be absorbed.
Right.
Why not?
Because
Why not? Very good question. Why not?
it's you need like a specific discrete amount in order to like be able to excite.
Exactly.
Yeah.
So this electron is unwilling to absorb the X-ray to even start to jump. Yeah. Why? That's how quantum mechanics works, right? The gap that exists here, this electronic gap that exists, says, okay, I will accept energies between this value and this value, because it's not really one, it's like a series of states back here. Okay. It says, okay, I'll accept anything that gets me to here, for example. And there's some delta in energy here. So this would be delta E. Okay. That delta E is determined by the material itself, depending on how you create this CCD. So that means that if I expose it to other forms of light, then it doesn't matter how energetic it is or how unenergetic it is. Only the form that is going to be accepted is the one that's here. Does that make sense? Okay. So we are by definition going to get visible light, right? Because we built it that way. Okay. So now I have individual electrons We spoke about this a little bit at the beginning of class. We said that we have these buckets, we collect the electrons. And so the next question is, a bunch of electrons becomes a voltage. How do I convert a voltage into a number?
Wouldn't it be like, you could do it like with capacitors maybe, so if you're like,
Oh, you're thinking physically. I'm just talking about like what properties do we want to look at?
oh, I mean, like, if you get like a certain value of voltage, you can you can set something up so that it measures something, you know, so like having a computer.
Voltage is a number, good. Yeah. So now I measure the voltage.
Mhm.
Okay. I need to know something to know how many pieces of light I got, right? That's the question I'm asking. I'm claiming that when you open up your CCD and you expose it to the sky, you get a number.
Yeah.
And that number says this thing was either really bright or really not bright.
Mhm.
But I'm telling you right now, we've gotten to the step where we measured only the voltage because we actually didn't measure the photons themselves. We measured the electrons. The electrons, yes, everyone understands, they create a voltage. Good, I measured the voltage. Now, how do I go from voltage back to the idea of light?
I guess if we have like a baseline of before we expose it to light, then we can measure the voltage difference.
Okay,
So there's like a frame of reference.
okay.
So going from like nothing to something, and that could be like how we vary.
Yeah, I'm just going to introduce you to a word called gain. Okay. Gain is going to be how we define the process of going from voltage back to a total number of light. Now, you don't know this already, but there is a 1-to-1 in the photoelectric effect. One photon comes down and it produces one electron.
Oh, okay.
Okay, but that electron, right, can sit in a potential well that you can vary. And you have done this before. You have changed the gain in your detector. Okay, what this means is that you are changing how many electrons recorded represent one photon. Okay, there's other steps involved, but the basic idea is this word gain. This is the property that you're changing. So you've changed two properties in the telescope, right? What was the other one?
Yeah.
Exactly, exposure time. So we open up the bucket, we let a bunch of photons fall, and then we close the bucket and we read off the voltage. And then we tell, you know, through some process, how many photons we collected. Does that make sense? Okay, I'm going to show you a little picture in here. I'm going to try and draw it good, even though it's not going to be drawn good. So this is the lambda. And this is in whereas this is the absorption. Okay. What the hell does that word mean? Absorption length here is referring to whether or not you are going to be absorbed. Okay. So down here is very good at being absorbed. Up here is not very good at being absorbed. So we can think about this in the context of how well do we turn a single photon into an electron? Well, that is going to depend on what kind of electron we got. Oh, sorry, what kind of photon we got, right? Notice that all electrons are created equal, right? They all have the same charge, but not all photons are. So we're going to have some sensitivity to different types of different types of photons in our electron count. So one thing that we have to understand, so this is specifically for silicon. Wait. SI, what is it?
Yeah.
Yeah, okay. What's silver?
AG. Yeah, something, yeah.
Okay. So you may see gain curves, and if you go to figure 3.2, which is the next one on the next page, it has wavelength again, like this, but now it's going to look like this, and that's like the sensitivity. So this is your gain curve or your quantum efficiency. Okay. And what that's basically saying is how well did you turn one photon into an electron, generally speaking. Does that make sense? Okay. We in fact observe things in the ultraviolet. So in order to do that, you will start with something like this, right? Should be like a CCD. And you can add something right on top of it here. You can add phosphorus. So you take phosphorus and you place it here in between, and you allow the UV photons to hit the phosphorus, and that phosphorus will then create visible photons. Not quite slowing it down, but converting it from UV into visible so that it can still be detected by the CCD. That make sense? No or yes? Okay. Yeah. Yes. Well, you sometimes will get more than one. So for example, if you have a phosphorus element and you hit it with an electron, with a ultra photon, what'll happen is you excite the phosphorus, and then so it absorbs ultraviolet, makes a bunch of excited electrons, and then they decay, and they can set off maybe 10 or 15 different visible photons. Right?
So that's like a unique or modified CCD.
Yes, that's how you could modify a CCD for ultraviolet.
Okay.
Right?
Does that mean that it's now only limited to that type of ultraviolet light, or can it also absorb the other light that's coming?
If you remove the phosphorus, you could. But the phosphorus is like a physical material, right?
Okay.
Right. So on
So-
what?
I got you. So it's meant for just detecting.
Yeah. It's how you could turn a CCD to be usable in other wavelengths.
Okay.
You can't keep doing that. So by the time that you get up to something like X-ray,
Mhm.
and you'll kind of see when we talk about this in E&M, by the time you get up to X-ray, this whole design doesn't work at all. And that's mostly just because the X-rays are moving far too fast. They don't care about materials at all. They go right through them. Right? All right. So the only thing that I want to show you afterwards, so you have these ideas of quantum efficiency. I'm going to need to delete some of this, but I'm going to get rid of this at the bottom first. Okay, that's the physical explanation.
Faster wavelengths, by the way, those are like when you go into blues and stuff,
What do you mean faster?
like I guess smaller.
Smaller wavelengths.
Yeah.
Blue, yeah.
Okay.
Yeah, sorry. Blue would be on this side.
Yeah.
Red would be on this side.
Okay.
Long wavelengths would be like microwaves.
Okay.
Small wavelengths are ultraviolet. Okay. So we wish the world were a perfect place, but it's not. Okay, so in practice, you have the number of photons here, and you have the number of data numbers called DN, or the number of numbers that come out. Okay, so at the very beginning, say 1 photon equals 1 data number, right? As an idea. Okay? So usually they fall along this beautiful 1-to-1 line. You expect that forever, right?
Probably not.
No, probably not. In fact, it's not. So we want to go back to this idea really quickly. Okay, this idea of a bucket. Okay. At the very beginning, the bucket is not very full. And it's easy to measure the potential difference. Okay. As I add more and more photons, what happens to the bucket?
Bucket gets filled.
Bucket gets filled. Very good. Now it's becoming more difficult, right? To measure the potential. And in fact, in practice, there is a limit. Right? What's that limit? We had a word for it earlier today.
Is it an astro word?
Mhm.
Oh, shit. I'm sorry.
Nick Reed said it. Saturation.
Oh, okay, cool.
Okay, so this is not magic. Just means the bucket is full. Right?
Does that mean when it hits saturation, it's just a flat line afterwards? Like it plateaus?
Well, think about it this way. Bucket's full. I add more photons, but they don't turn into anything, right? Exactly, right. So given a bucket's capacity, right? Let's say it has some potential difference of 0 to 50, right? You put on electrons, you put in electrons, you put in electrons, you fill it up until it's 0, right? Now I can't measure a difference in the potential. And it can't be overflowing because it's a real physical bucket, right? It's an actual object, right? You're not going to then measure a plus voltage on the other side. Okay, so that's the idea of saturation. And I said, in practice, we would like it to act like that, but nothing works the way we want it to. So in fact, in reality, this is what happens. You get less and less reliable information, right? So that's the expectation, but you can absorb more and more photons without it actually hitting saturation. So usually what we try to say is that about 90% of saturation is where you should believe your results. Okay. This is a form of systematic uncertainty. This is something wrong with the physical objects, right? Not something that we can just average away and get rid of. Okay. So one of the first experiments I asked you to do is to play with gain and exposure time in order to measure whether or not you're saturated. Okay. So that's the reason why we're doing it. Okay. Let's see, what other thing do you have to know about? Okay. Hey, Reddit. Oh my goodness. And so we talked a little bit about collimation last time, or at least at the observatory, we've talked about that a lot, right? Remember what that word means? Changing the tilt of the mirror such that? Yes, exactly right. So this is the idea. Let's do the diagram again. I know it's been a while. So here's the tube, okay? The perfectly drawn tube. Don't say anything about it, right? Okay. So the light comes in from infinity, and the beams are completely parallel, right? Okay. Then it hits a concave mirror, okay? And it focuses that back over. Maybe I'll get rid of this one. It's perfectly parallel, okay? It focuses it here at a box. So I can follow those all the way back. Like that. Right? Okay. So you may have seen, we had some discussions about like using different eyepieces, and you can see Saturn either bigger or smaller, or bigger field of view or smaller field of view. So a couple different words we have to introduce here is the idea of a field of view. So what does that mean? That means when I'm using the telescope, how much of the sky am I seeing, right? And in particular, you're then going to take an image, okay? And that image is going to have a fixed size. So this square here, so zoom in on the square, right? Has a fixed size. What's the fixed size of the square? Anyone know? But that's the question, right? How many pixels? So this is some number of pixels on one side by some number of pixels on the other. Okay. We can't do this on our telescope, but if I moved this forward and backwards, right? What would that do to the picture?
Assuming like,
Assuming that you could focus it and it had a new mirror.
yeah, like, it would make the image.
What's that?
But that way.
One of the two ways would make the physical picture bigger, right?
Yeah.
Okay. So we recall that from optics, there are magnification measurements, right? And you can go into your night book, you can pull out the one for a telescope, and it says how far away the object is, gives you this much magnification, right? Okay. You can also look at the results that you have. And the very first thing you want to derive is what's called the plate scale. Okay, and this is the, by definition, how large a pixel is on the sky. Okay. Is that possible? Yes, very possible. Okay, so this was your first experiment. 1. Here's your second experiment. 2. Deriving the plate scale. Okay, how would you do this?
Trial and error. Experiment.
No, so we're working together, right?
Okay.
I'm gonna give you the answer right now, obviously.
We're supposed to have already done
No.
Oh,
I'm giving you a task. No, I'm giving you a task right now. So you can do this from any observation that you've already taken.
Okay.
Reed and I did this together, but he doesn't realize that we did this together. What? You remember? Okay, so what do you do, Reed?
Yeah.
Yeah, Reed.
Yeah.
Yes.
Take the shot. Remember writing it down.
You use geometry. Very good. Okay. So we're going to do a couple different things. Stars in the sky. Oh, this is awesome. This is
So perfect. This is already.
no. That'd be too complicated. I don't want to do that. Okay. So this is the way the real sky is, right? And let's say it's Tuesday and I look out and I'm like looking through this. Let's look for something I actually know.
Looking from the outside, like the alien.
Don't tell anyone. Okay. So let's look over here for here's Betelgeuse. Okay. And I can read this off here. Betelgeuse is like near 6 hours or 270 degrees declination. And it's a little bit north, so it's a little bit less than 10 degrees. Okay. So I have the location of Betelgeuse.
Is the whole for point?
No, it's for sticking your hand in so you can
Ah,
move
okay.
this around. But I'm using it in that way. Is that
Ah,
okay?
okay, yeah.
Okay, so there's Betelgeuse, and what's the other big one in Orion? Does anyone know? You don't know?
Bigger than Orion?
No, there's 2 big ones. All right, let's draw Orion in our little picture.
Orion's belt? I don't know.
That's the next star and-
Oh, it's probably like a
Alright.
number. I was gonna say I think a number. Letter. Name. NCAA.
Yeah.
Yeah, but then you follow it up with this number.
Okay. You familiar with this constellation? It doesn't have the lines in real life.
Okay.
You know that, right? There's no lines. Okay.
Is it an Archer?
This is Orion. It's a really good drawing of Orion. Yes, he's an archer. Okay. Right. Have you seen this before? Seriously? Okay, your homework Thursday is to go out and look for Orion. It won't rise until like 8 or 9. Okay, but it'll be in the west. And it's gonna look like that. Yeah, these 3 dots are probably one of the second most famous, if not the most famous, dots that you see in the sky. So that's Orion's belt. They're grouped together like that, really close, right? And up here is Betelgeuse. Betelgeuse is red, very red. And this one here is Rigel, and it's very, yes, correct. It's a blue. Okay.
Don't really take a picture of it. I think it's actually.
Well, your homework is to, I'm using Orion as an example, but you could do this with any constellation, right? So I could take Rigel and Betelgeuse, and I know their locations. I go into Stellarium, I find the RA in the deck, and I go to Rigel and I find the RA in the deck, right? And then I look in the notes for how far away they are on the sky, right? Because one of the very first things we did was determine how far away something is on the sky using spherical coordinates. Remember that? I know it was like 17 weeks ago. It's in the notes.
Yeah.
Second week or third week. Okay. So now I have these 2 locations and I have some physical number of degrees between them. So now how do I relate that to my picture, my pixel picture?
Well, it's not on the edges, but you know, like how far apart those things are.
Right. So I could just do something like this. I know this is going to be gross, but. Right. So I can find the center of Rigel. I can find the center of Betelgeuse. And I'll know where they are in pixel space. And now all I need to do is find their separation in pixel space. And that'll be with Pythagoras' theorem, right? We take the difference in their x's, we take the difference in their y's, square those quantities, take the square root, and that's the number of pixels between them. Okay. So that would be, this one here, would be the total number of pixels between them. And I just calculated, right, the distance. So using, I think it's like week 2. I calculated how far they were in degrees, right? And the plate scale is that ratio. Does that make sense? Okay. So this is going to give us metrics for how big our field of view is. And you can then tell me how big is the EV scope field. Okay. That is your homework. Is that reasonable? Questions about that? If one of you does it, and then you just send the answer to the others, I'm gonna shake my fist at you.
Well, okay.
You can help each other, but you all have to learn how to do this, right? Because we're gonna do 3 different important tasks. We're gonna use Stellarium to determine where things are supposed to be in the sky. And then we're gonna orient to our observations, right? Okay.
So we're taking like a flat image of something and just trying to find out how far apart they are on the projection of the plane. Not necessarily like the depth
Oh yeah, no, we don't have any information about that. The world that we live in is everything's projected onto a sphere like that,
Okay,
right? It all appears at the same distance.
is there a way to do that, or do we not have?
Oh yeah, of course there is.
Okay,
But that's not this class.
got it.
You would need to know the flux of the star. If you had the flux, you could get the luminosity. If you had the luminosity, you could get the distance.
And then you can actually know,
That's how we know.
Taking the numbers that was represented on screen. And from that, you know, physical distance.
When we say physical distance, we're not going to say tens of kilometers, right? We're going to say, how much of the sky am I seeing? So for example, if I ask the question, you know, can I see both the Orion Nebula and Saturn in the same image? And they are 7 degrees apart, right? If I knew ahead of time how big my field was, my field's only 2 degrees by 2 degrees, then I'll know I can't see them, right? Because even though 2 by 2, still less than 6, right?
how much is 1 degree again? Is it like,
How much is 1 degree?
yeah, like.
Oh, on the sky.
Yeah,
I think a half degree is your finger.
okay,
2 degrees, I believe, or 2 fingers is, I think, 1 degree.
okay. And then.
So this is like 5 degrees.
Okay, that's right.
Right.
And this is like 1% of the sky? Or no, that's not right. No. What was the fist? There was a fist thing.
10, or no, 2 fists, I think is like 10 or something.
Okay, okay. Sorry.
I forget how this goes, but we can
Yeah.
map it out, right? I could go 1, 2, 3, right? You go all the way around.
Okay.
Makes sense.
Do you want us to do that type of observation as well, or do we just look it up?
No, no, no.
Okay.
We're gonna use stellarium, which is exact.
Yeah.
Okay. We're not gonna eyeball it. Okay. No, we can't. We're not gonna eyeball it. Okay. So the other thing you may find, maybe these two are too far. Then what would you do? Maybe I chose Rigel and Betelgeuse on purpose, and they're too far to fit into one picture.
Like we can't see it on our plane.
Yeah.
Is there a way for us to like adjust our telescope to be able to do that, or is it just?
You tell me.
Pick something else.
So to answer that first question, the right answer is pick something else. But to answer the first question, can I change the plate scale or the factor by which a pixel on the sky is represented on my telescope?
Is that moving later?
You can't move.
I can't move the mirror, right? Only thing I do if I move the mirror closer or farther is I unfocus it. If you go and you look at your night book, you'll see the magnification is based on the curvature of the mirror.
Is it replace them?
So you'd have to replace the curvature of the mirror. We're not going to do that.
Is that expensive?
No, we're not going to do that. That's not what the class is like. So it's interesting because I think if I had taught this class like 40 years ago, before computers were common, the way that you were supposed to do this, people would literally go and they would grind their own lenses in undergrad.
Nice.
So you would start with a piece of glass and then you'd bevel it down and you'd build a physical telescope. I mean, you can ask Catherine Gray if she'll let you. Dr. Gray would probably welcome someone to do lens grinding. But typically speaking, they're not as, right? The reason why we do it this way is because this type of mirror and CCD is much more portable than the multiple lens that we used, right? So if you look at the old telescopes, the ones that look like spy glasses, they're all significantly longer because you have this one needing to focus here, and this one grabbing it and pulling it out on the other side. And if you use the telescope like this, you fold it on itself. So you can get half of the length for the same focal distance. Did that make sense? Open night up again. There's a whole section on this. Okay. If you want to, you can grind your own lenses, but unfortunately, that's not part of this class. Okay. You want to? All right. There are some processes that we won't have to do, which is very convenient. When we use the big telescopes, if you ever do end up using the big telescopes, one of the first things that you have to do is you take a dark frame. And you say to yourself, I don't know what that is, but I always have to do it at the beginning of the EV scope too. But with a big telescope, you'll then point it to a part of the sky, which is uniformly illuminated, and you'll take an image. And we don't do this with our little telescopes, mostly because we don't have the ability to. There is a form of image stacking. Flat fielding, essentially what it does is it demonstrates where in the CCD you're going to have a problem. So if you give it uniform light and you take a flat field, you can see whether or not certain pixels in one region or another, whether they are biased to creating more or less electrons, right? Maybe this part of the manufacturing process created more electrons over here. So you take a flat field, and that way you can divide it to get the right amount of photons everywhere. Does that make sense? This is built in to the EV scope. They don't like let us do this, but in practice, you'll always have to take a flat field when you use the big ones. Okay. So now let's talk about the dark frame. What the hell is a dark frame? Because you put the cap on, right? And then you press this button, it says take dark frame. So what the fuck am I doing?
Control.
Just controlling you?
Oh, meaning like, no, like a control, nothing, no light is being applied to it, so we'll see what it looks like.
Seeing what looks like.
I guess like the background, yeah, like how boring is it without any light?
Okay, and the expectation is that it should be?
Not, yeah.
Should be 0, right? But nothing ever works as we expect it to, right? So what is actually happening? That it is not 0.
It's like faulty material.
No, caps on, perfect.
Yeah. I don't know, I guess the limitation.
Do you measure photons?
Do we measure?
Not personally.
No, in fact, we don't personally measure photons ever. What do we measure? Well, actually, our eyeballs do measure photons, but that's different. Okay. We measure what? Electrons.
Yeah.
So now we have to consider all of the different ways in which photons, right? Photons make electrons directly. Okay. But electrons can just be produced.
So could it be like, I guess, pollution from the device itself?
Right. So there could be this band gap, right? We make it, it's perfect, but it's also warm. And there's thermal energy in the system. And sometimes that thermal energy can be enough to send an electron from one to the other. Because if you remember, who's doing stat mech right? That it? Okay, everyone. Okay. Everyone has taken stat mech, right? Okay, so what is a plate scale? Can I delete some of this
Yes,
since I've ranted enough?
deleted.
Okay, let me ask you a question. What is the distribution of velocities for a given temperature in a material? Okay, let me say that again. Here's velocities, V. Here's the number of them for a specific temperature, T equals 300. What does it look like?
So that probably. That's, you can like it's stochastic. Oh, Jesus.
Oh, no. Number of,
The number of objects moving this fast as a function of how fast it is. Is it equal on both sides? Centered around some value?
Oh no. Oh, wait a minute. Isn't it like something like that? Or the other way? Sorry.
nope.
Okay, is it like this?
Oh yeah. Yeah, I think so, right? That's the oh shoot. It's like the Dirac.
What's that?
I don't know, will they go faster than each other?
Okay, so sometimes they hit each other, right? You can have a collisional group, and that can speed them up more than just the 300. You can also slow them down, right? Let's think just of a gas for a second. You have a gas currently around you, right? There's tens of billions of air particles. They all have a speed, right? Which on average is the speed of sound in here. But does every single one have the same speed?
No.
This is velocity versus number of particles.
How many particles have each velocity?
So like a given number of particles.
Mhm.
So yeah, that,
So this is right?
I think so.
I think so. That's like the
I'm
most likely.
Right.
Okay.
That's what I was thinking. Yeah.
All right. So you're going to look at tonight Maxwellians. Hey. So this might have been what John was alluding to. It does have a peak, and then it falls off, but it has a long tail. Okay, and it's not centered around the center. It's not equal. Okay, so this might be the peak, but there's very little stuff that's actually going zero because it has finite energy. So this falls off much more quickly than this side, where you can find particles out here, a significant fraction are actually going very fast, much faster than the 300 Kelvin would allow. Does that make sense? And this is true of all materials, right? As long as they're collisionally in local thermodynamic equilibrium.
Is the dotted line representing room temperature?
This is just some peak.
Okay.
Yeah, I gave 300, but it's a,
Okay.
I'm not a plotting calculator.
Okay.
Yeah. Okay, so the fact that you have a long peak here means you do have some particles which are moving very fast. Okay. Now, if they collide with a silicon atom, it turns out that you can also get it to give up your electron. And that electron will now have enough energy to make the band gap. So you've suddenly created voltage from not a photon. This is dark current or dark charge. Okay. So thermal heat from the Maxwellian creates source of electrons. Does that make sense? Okay.
So that's why it's preferred to do observation when it's cold.
Yeah, I mean, it'll happen either way, right? If you can get that T down, right, then this wing comes backwards. But no matter what happens, you're still going to have a wing that goes out to really high temperatures. There's just very few of them, so we don't notice them. But if you're specifically measuring for electrons, particularly if you have something like a high gain, how is that going to affect your darker current?
Yeah, but like
Say that again?
For sense.
More sensitive. So your gain's job is to amplify the number of electrons you got into representing more photons. But if you have a very hot detector or you have a ton of dark current, that gain is also applied to those not real, photoelectrons. Does that make sense?
so when we say high gain, are we saying our bucket is taller so that it can fill more electrons, or
Bucket's the same size.
buckets the same size? Okay.
Bucket's the same size.
So so sensitivity.
Yeah, gain is basically saying, I mean, this is a little complicated with how you read them out. The Physical aperture size is never going to change of your CCD, but what you can do is you can change the depth of the potential well, so that every electron that's added represents a different amount of the potential well being filled up. Is that what you meant?
Yeah.
That'll be your gain versus your sensitivity.
Mhm.
Okay. Okay. There are levels of uncertainty added here. You know, when we go into the process of thinking about how many photons we got, we have to work backwards through that entire step, right? Because the number that we get out is like 7. Okay, well, what the fuck does that mean, right? No mathematical number should be presented without
Without units.
what? Units, good. That's the first one. So number of photons, good. What else do I need to represent it if I'm going to submit it to a journal? Uncertainty,
Oh, no.
right? So in fact, we have to say something along the lines of, oh, that's the gross one. Where did I put the good? Oh, here it is. Okay. So when I report my results, I have to say result plus minus uncertainty. I almost got it. Okay. So generally speaking, we talk about this in the context of what is known as the signal to noise ratio. Do you recall me talking about that a couple weeks ago? Okay. And we said that signal to noise ratio, signal divided by noise, is what you want to report. What's an idea of what's considered a good signal to noise ratio?
Small noise.
Oh, but what number? We just use numbers, right? So signal to noise ratio, actually, like a signal to noise of 1, is that good? No, it is not good. It's too good. Raise your hand for 2 is good.
I guess it's better than 1.
300 is great. Okay, so there's something in between 1 and 300. Good.
Yeah.
150? 100 is far greater than we ever normally get in life.
That's shit.
So usually 3 is okay.
Wow.
So this is pretty surprising, right? So what does this mean? This means that let's say I have some measurement, and let me show you what I mean by why 3 is okay. So let me show you the signal, and then I'll show you the noise. Okay. So let's say this is just like an array of pixels. Okay. And I'm reading it out. So this will be brightness, B up here, brightness. And this is just like the pixel number. So like, let me do X, okay, from left to right. Okay. Here's 0. And here's like 100, 110 for some reason. Okay. So give me like a pixel noise level. 2? Well, I'm gonna take 12. Okay. So that's like right here, right? So the first one's like here, it's here, it's here, it's here, here, here. Very few of them are actually going to end up exactly on 12, right? Because the background, the stuff that we're measuring, is going to have some fixed value. We look up at the sky, we look for where there's no stars, and we still see photons. That's the sky background that we've talked about before, some average, right? So here's an example. Let's say this is the background that comes from the fact that the thing's hot, right? Just looking at the detector background. Some of it's going to be more, some of it's going to be less. And it's going to change every single time I take a picture because the thermal conditions are constantly changing, right? So if I told you, hey, I think that's my signal, what would you say to that?
How do you know?
Yeah.
you explain the axis of the graph again?
Yeah, this is brightness. And this is just position on the detector. So imagine I take some strip of pixels and I'm just looking at them now. And I'm looking at them as a pie graph or as a dotted graph, left to right. So here's my entire detector. I just took a strip out and I'm just looking at the brightnesses. So some of the values are low, some of the values are high, right? They're mostly around 12. If I take the average of all of them, they're around 12. But this one I said, that's a star. Do you believe me? Why not?
Like the highest number, highest value, so you're not seeing this top one.
Yeah, you're not taking into account the other one. So we want to compare, for example, what I claim my signal to be. That would be S. So here, let's read it off. You know, if this was 12, this would be 24. Okay. It's a little less than 24. So this one's S is maybe 20. Okay. And the noise that we claimed earlier was 12. So therefore, signal to noise ratio is
Bigger than 1.
and smaller than
2.
2. Good. So it's about 1 to 2. So is this believable? No, it's not believable. Anything less than 3 is going to be really hard to convince someone that that's a real result. Let me show you the difference. Okay, let's erase that. We'll do it again. What? What?
No.
Okay, so now this is 36. Okay, let's put this value up here.
Okay.
See it yet? Does that look like a signal?
That's probably a signal. Actually, now I see it.
Now you see it, right?
All right. Got it.
So the scatter here is very small. The background, maybe not so big, right? You'll need to characterize that background. Sometimes you need to do uncertainties in the background and that comes into your analysis. But generally speaking, you can just look at the points. There's one point that sticks way up outside of it. Let's say it's like out here, right? Is that a real signal?
No, I'm just kidding.
No, definitely, right?
It's probably, yeah.
It's probably a real signal. There are other ways to do this, right? And you'll see this in practice, especially if you have a physical explanation here. Let's say you see grouping, because we see that our stars are not just point particles, but they might have a finite shape. So if this one had a friend here and a friend here and a friend here and a friend here, right, that you could like see in your mind, it would be like a little point sticking out, right? Whereas this one didn't. Right, then you might be a little suspect of that guy. I don't know what happened there, but maybe that's garbage and this is real, right? So we're going to use 2 different types of metrics to understand this. The signal to noise ratio here is the first one, the most important one that we start with, which is how much signal did we have divided by how much noise we had.
Is this something we can actively do, or is this like after we record our information?
No, unfortunately, this is in what we call the data analysis stage.
Okay.
So you'll have all the signals, right? And you'll see them. And like, oh, bright. I see bright here, right? So you can see that bright spot. Dot. Boom. Good. But you might also, while it's projecting on the screen, you might see like a green pixel. Like that's not right. That could be this guy right here, right? Just a random 1 pixel that seems to be blown out on the detector. Yeah.
It's more like an uncertainty rather than like a correction. Now we have to do predictive.
Yeah, no, right now we're not talking about any sort of corrections, right? So in practice, the EV scopes, they're good out of the box, right? They need to be wielded well. They need to be used well, I should say, but they don't require additional post-processing that you would have to do for any of the larger scopes. So larger scopes will require multiple steps that we'll have to talk about and train you on if you ever want to use the big ones. If they ever fucking work. Right? Okay. So in practice, the hardest part of your job is determining N. What is the sources of uncertainty and how do I correctly add them together so that I can give the result S in the context that it matters, plus minus N. Does that make sense? Okay. So we'll come back to N because I don't want to just bombard you with facts. That won't do anything for your brain. But this whole discussion is in the book that everyone owns, right? Everyone owns it, right?
Yeah, definitely.
No. I don't know where this is. I just took this from Laura, I think. This is Dr. Whitney's book. Doesn't have any of my notes. Someone has a lot of my notes. I don't know who it is though.
Your book?
I lent it to someone and I forgot to get it back from them. I don't know where it is. Don't look at read. Okay. So this is the process SNR. You may hear it said SNR. Have you ever heard that before? SNR. Yeah, that's silly. It's just signal
Noise ratio.
Yeah. Okay. I'm just writing it out. Full like words. Okay. So that's the SNR. Okay. Not S divided by N always, but this is the meaning. Okay. Questions, comments, concerns? We'll talk about adding in quadrature probably next week. Generally speaking, the beauty of any Poisson process is what property is true for a Poisson process.
What is true about it?
Yeah, right. This is the coolest thing about a Poisson. What is a Poisson process again?
Like,
Let's dial it back.
when you're like measuring a whole bunch of different like time periods or whatever of the same thing, and then you're comparing it to each other, is that
Okay, by definition, a process is Poisson if it satisfies the following types of conditions. 1, the measurement of the events are independent of one another. They result in whole integers. You can't have a half of a photon. And they're uncorrelated. So the presence of one photon does not create a second photon. Okay. So they're physically independent, they're uncorrelated, and they occur in integers. Right? So that makes this a Poisson process. It has to be random, it has to be stochastic, right? Something that's being generated has to be random in order to be Poisson. Okay. So the explanation that I always talk about when we first introduce them is people in front of you at a Costco, right? While you check out. There's always an integer number of people, but the rate may vary, right? So you can say, well, if this is controlled by a Poisson process with some unknown rate, maybe 3.5 people are always in front of me. Sometimes I'll get a larger number, sometimes I'll get a smaller number. And every single time I go to sample it, I'll get a different number, right? Okay. The result of a Poisson process is always that the signal to noise ratio
is good?
No, it's not that it's good. Okay. So we'll say that the signal, okay, is the number of photons I get. Okay, and I'm going to do number gamma like that. The cool thing about this is the uncertainty in the Poisson process, N, is the square root of the number that I got. So therefore, the signal to noise ratio is
It's,
You can tell me. Go over to what? And again. Wow, no one sounds impressed at all. That's really cool, guys. Come on. Yeah, not for me, for Poisson.
well, hang on. So just to be sure then, we're saying we can use this approximation? Or is this
If
always right?
If the process is Poisson,
Uh-huh.
then this is always true.
Okay,
Now, we'll talk about the ways in which n is going to vary when we talk about all of the different sources of uncertainty. And then we'll have to discuss, for example, how uncertainties are added, right? So what I'm saying is that this piece here is the uncertainty from the Poisson process, sigma p, okay? The noise from just the fact that the Poisson process exists.
okay.
So if I measure 100 photons from some source, what's the uncertainty on that measurement?
Square root of 100.
So it's 100 plus minus 10, which is a signal to noise of 10. Very good. Cool, right?
Okay.
So you can already start looking at your data. Okay, you have numbers. Now, they are not numbers that go from 1 to a billion or 1 to a trillion because they're normalized. And we don't know what the normalization constant is. These numbers that you have in your CCD go from no one's looked at the numbers, huh? What?
Yeah.
Oh.
Yeah. The one graph, that's like from 0 to 1.
That's correct.
Oh, okay.
The numbers go from 0 to 1.
Got it.
What? Okay, so this is a fucked up thing that I have to tell you. Okay. On your phone, okay, when you take a photo, okay, you have 2 options. Oops. Yeah, that's 2. Okay, this will count. Okay. On one hand, okay, your camera will do one of 2 things. Okay, it'll take all of the photons that it collected, it'll turn it into a voltage, and then it will report to you numbers that are given to you in one of 2 ways. On one hand, it'll tell you a number between 0 and 1. Like, what the fuck? Okay, that's not very nice. On the other hand, it will tell you that it's between 0 and 256. So how do you think you get from 0 and 256 to 0 over 1?
Multiplied it by 256.
All the way around.
Oh, okay.
At the very beginning, almost all computers only measure from 0 to 256. And someone was like, let's just divide by 256. Okay. Why 256? What's special about 256?
Pixels.
It's 2 to the something.
It's 2 to the something
Yeah.
because it's a number of bits.
Yeah.
It's a storage space. So the original one, that was the original storage space. And then for convention, they just kept it. Even though we can store much larger numbers. And in fact, you saw in computation, you can store numbers, if you do it well and you build the onboard processing, you can collect an exact number of photons to a great accuracy, right? So you'll see that if you ever use other spacecraft data, if you ever use a traditional CCD, they won't have that cap. But if you ever just pull out your phone, this is a memory saving device because these are very big objects, right? So they don't want to remember tons of numbers. They want to remember however many digits they need, and then they throw out the rest. Does that make sense? Okay. So you will now you open up your photo, you're going to look at it, you're going to do this when you get home, right? Or maybe tomorrow when you're tired of listening to me. Okay. And you're going to see it goes from 0 to 1. And you're going to look at some value. Let's say you cut across it and you say, well, I got some peak number. Okay, that peak number was what? Let's say 0.3. What's the signal to noise on 0.3? I'll make it easier. What's the signal to noise on 0.3333333 repeating?
So much easier.
Okay, let's do it a different way. Let's do 0.9.
Okay,
What's the square root of 0.9?
probably, yeah.
That was
Would it just be the same thing? If we got the highest signal, then the signal's noise should be the same value? If we did it right, or?
It's not the same value, right?
Okay,
It's the square root of the value.
okay, square root of the value, that's what it is.
What's that? Yeah, it's like 0.3, right?
Okay. Now I see what you're saying.
Were you saying the number of pixels? What were you saying?
So I was saying if I measure something with 0.9 brightness, what's the uncertainty?
0.3,
And what's the signal to noise?
0.3.
See?
My paper's just gonna say 0.3.
No. But now you can create, so let's say you have an array, a square like this. Let's ignore everything that's going to be more complicated. If you wanted to create an uncertainty array, where you give the uncertainty for every single location, what would you have to do? Square root every point, correct. You see? And the interesting thing about the square root scaling, so let's say I take the square root of 10. What's that?
3 point.
Yeah.
Yeah,
Some
okay, 3 point something,
math.
good. So 3.1 maybe, okay. And let's say I take the square root of 4. That's 2, right? The difference between 2 and 3.1 is not double. But the difference between 10 and 4 is more than double. So generally speaking, your square root array, the uncertainty array is going to be flatter.
Okay.
You see, it's not going to be anywhere as peaked. It'll have exactly the same features, obviously, because it's the square root of the other one. But now you'll be able to see that the more signal you have, the better, right? So your whole image is going to look like that uncertainty array in signal to noise space. Does that make sense? Okay. Okay, so before I start bombarding you with actually how we calculate noise, I think we're just going to pause it there, right? Because I've just said millions of things to you. What kind of questions do you have?
If you want us for next week, figure out how big the EV scope picture is and also the signal to noise ratio.
Well, signal to noise ratio you can do for free, right? The most important thing that I want for next week is just the scale length of the plate scale of the EV scope, right? And what that's going to do is it's going to force you to do 5 things. 1, download the data. 2, open Stellarium. 3, determine the distance between 2 stars. 4, determine the center of those 2 stars on your image, and then find the distance between them in pixel space. Once you have those 2 numbers, you divide them and you say, Krismani, I did this, and I'm so happy that you made me do it.
So,
No, you're not? Okay. It's not that much data analysis though, right? It's 5 steps. Okay. If you want to, you can then begin to look at the data itself. Take one of those images, take one of the green ones or the blue ones or the red ones or whatever you want to do. Look at the data. You know, you may find that it goes between 0 and 1. Oh, interesting. What does the signal to noise look like? Well, I can multiply that entire array by square root. Okay, now I have a picture of the signal to noise ratio, right? Okay, questions, comments, concerns?
so the closer it is to the Photons process, the more we can trust the data we report.
Yeah, let's not read into that because I'm already gonna fuck it up next week. But what
Let's not read into that.
I mean, we didn't talk about gain.
Okay.
We didn't talk about sources of other electrons, right? In practice, we won't be able to do a lot of that analysis because we don't have a dark frame, we don't have a flat field, but you need to take into account all of the other sources of background. Right? Okay. I'm just saying for first principles, this is how we treat Poisson processes.
Okay.
Usually I'll tell people, okay, how many measurements do you have to make of something in order to be confident that you know what the number is?
and 10 less than like 20.
How did you guess that? Vibes don't count. This is a physics class.
I mean, one's,
Yeah.
one's not enough.
One's not enough. Good. Yeah, one's not enough for sure.
Say more than 9. You can just get rid of 9.
Okay.
Nice.
That's the number you want to take. You see? Poisson process. Let's fucking go, boys. Right? Does that make sense?
16 then.
No, 9 is fine. I always say 10 because it's round. I don't like 9 as much as I like 10, but 10 is fine. 9 is fine. Okay. Measure anything 9 times and you'll get it right. Now, if you're measuring something to cut it for wood, obviously. Once.
Measure one.
Just once. Cut immediately. Okay, any other questions? Okay, so I'm going to stop the recording here.